Hello students, welcome to lecture 35 of this online course on Nanophotonics, Plasmonics and Metamaterials. Today's lecture will be on lithography and pattern transfer. So here is the lecture outline. We will first look into the overview of this topic. Then we discuss about different lithographic techniques. As you can see, we will discuss about photolithography techniques and non-optical lithography techniques. So this photolithography can also be called optical lithography techniques. And then we will look into the pattern transfer methods like wet etching and plasma etching. Okay. So overall this particular topics will be briefly covered in this lecture. Now in the previous lecture you have seen that we have covered different methods of depositing thin films. Now we will look into the methods or techniques related to lithography, where we are able to make some patterns on those films, okay, or in the substrate itself. So lithography is the process of applying a pattern onto a substrate surface, which is later transferred to the substrate itself. So optical lithography or photolithography, as the name suggests, it uses light to replicate a pattern, and the pattern is actually made in the photomask, and from the photomask you are basically transferring that pattern onto the substrate. So this is typically very similar to the traditional photographic reproduction. Okay, so you can think of those methods and you will find an analogy here. It involves a photosensitive polymer, which is also called photoresist, that is applied to the substrate. Then it is exposed to light, and it is exposed to light via the photomask. So only those portions which are to be printed, that particular pattern is formed in a way on the photoresist. So that actually gives you a patterned photoresist. So we will go into more details of the photoresist in this lecture only, and we will tell you about positive and negative photoresists. There are different types of photolithography exist, which are called contact, projection, immersion, interference methods, and they also use different types of lights, as you can see, UV, deep UV, extreme UV, X-rays and all these things. So there are applications for each of these. So what varies here is basically the wavelength, so you can understand the feature size that you are trying to develop will also shrink as you go from UV towards X-rays. Besides optical lithography, there are also non-optical lithography methods which use electron beams. So this kind of lithography is called electron beam lithography. There are lithography that uses ion beams, which are also called focused ion beam lithography. There are methods like where mechanical forces are applied to create pattern on the resist film. This kind of method is called nano imprint lithography. So we will briefly look into all these different topics in this particular lecture. Now you have to keep in mind that each lithography technique has its advantage and disadvantage in terms of the resolution, throughput, suitability for different applications. That is why all these different methods have been practiced, okay, depending on your need and the application demand. So when we look into photolithography first, okay, it tells you that photolithography means light is involved. So you can think of the light sources, and popularly UV light sources are widely used in photolithography, and that is because of their ability to provide better image resolution and the availability of UV sensitive photochemicals. Okay, so these are the main two reasons. UV, as you can understand, these are high energy, okay, as compared to the visible, so they have shorter wavelength. Okay, so mercury vapor lamp are dominant UV light source in photolithography, and they are able to emit lines at 405 nanometer, which is called H line, 365 nanometer, that is I line, and 254 nanometer. Now remember that among these three, the 365 nanometer or the I line is the most commonly used one. Now, deep UV light sources such as excimer lasers, which are operating at 248 and 193 nanometer, they are also adapted to achieve higher resolution. So, shorter the wavelength, okay, deeper you move into the UV, you are able to achieve higher resolution. Now, if you look into excimer lasers, these are basically short form for excimer dimer laser. It is a type of laser that generates intense ultraviolet light via the use of excited dimers or molecules. Unlike most lasers that rely on stimulated emission from atoms or ions, excimer's lasers use a combination of noble gases and reactive gases to create a laser medium. So, extreme UV sources are also under development, which operate at 13.5 nanometer. So, they will be used for advanced lithography applications. Now, in lithography, it is crucial to ensure uniform illumination intensity across the entire substrate surface, which requires shaping the beam into a flat speckle free pattern to avoid undesirable effects. So, this is one of the requirement of getting a good lithography, photolithography. So, when we talk about speckle free pattern, so speckle free pattern is basically referring to the desired outcome of the lithographic process, where the pattern or the image that is produced on the photosensitive material or photoresist is free from the speckles or unwanted noise, you can say. So, speckles, when you think of speckles in lithographic pattern, they can degrade the quality and the precision of the final image, especially in applications where you actually aim for high resolution, okay, such as in semiconductor manufacturing. So, those are the cases you need to make sure that uniform illumination intensity is available across the entire substrate's surface. So, this is typically the process of lithography. As you can see, you have a silicon substrate and you have a thin film deposited on this. So, we have discussed the methods of thin film deposition in the previous lecture. Now, after that you can spin coat a photoresist, that is a chemical, and then you have this particular chrome mask. It is a mask made of chromium. So, you can see there are openings in the mask, and then when you expose UV light to it, UV light rays are blocked where the metal parts are there, but it can actually go through onto your photoresist where the masks are open, okay, and that way you get these exposed regions. Okay. Now, if these are positive photoresist, when you develop it by etching out this particular things, you will see that when you develop a positive photoresist, these parts actually disappear or they dissolve. So, you are left with this particular pattern, whereas if these are negative tone photoresist, you will see that this only remains, the remaining parts actually dissolve. Okay. So, as you understand here, the photoresist basically composed of a photoactive compound, a resin and a solvent. And how do you apply photoresist? As I mentioned, spin coating is commonly used to apply photoresist on the substrates, and solvents are removed through heating. And once you expose them to UV light, the photoactive compound, it releases chemicals that increase the solubility of the resin. So, it makes it either positive or negative tone photoresist. So, once again, if you have positive tone photoresist, these exposed patterns are dissolved, they can be removed, and if they are negative tone photoresist, these particular patterns they stay and the remaining photoresist can be dissolved. Okay. So, there are important parameters in this process, something like what should be the exposure, the light exposure and the dosage. Okay. So, you can see the exposure in photolithography is typically measured in millijoules per centimeter square, and exposure is calculated by multiplying the illumination intensity, that is given by milliwatt per centimeter square, by the exposure time. So, that gives you the exposure, and the typical dose value for photolithography ranges from 50 to 500 millijoule per centimeter square. So, that is the range of the exposure that is needed for photolithography applications. And the nonlinear solubility dynamic range in photoresist provides this excellent contrast in photolithography, and as you can see here. And when you talk about photoresist, there are two types. So, one is positive, one is negative. So, the negative acting photoresist, they behave completely opposite to the positive tone photoresist. So, in the case of negative tone, they reduce the solubility after exposure due to some polymerization reaction. So, they do not get dissolved when you try to develop them, the remaining parts get dissolved. Okay. So, deep UV wavelengths result in reduced photosensitivity due to resin absorption, and chemical amplification mechanisms can be used in deep UV lithography, where a single photoacid molecule catalyzes multiple reactions. And photoresist for extreme ultraviolet lithography are less common, but they are still in development due to the unique challenges. So, you can understand that extreme UV lithography is still not very popular because the material that can help this particular technique is still under development, whereas the UV lithography ones are well developed. Even the deep UV lithography ones are also available. Now, another important component that you have seen in this process of lithography is the mask. Okay, you can call it simply mask, photo mask, or its chrome mask. Okay. So, what are masks? Masks are basically these are glass substrates which contain opaque metallic patterns, and these patterns are typically made of chromium, which are supposed to block the UV transmission. Okay. So, the creation of photo masks involves standard photolithography process, including applying photoresist, exposure, and patterning the patterns of the underlying chromium layer. So, that way you obtain one mask, and then you can use that mask to create many such replicas, right. And UV laser source such as helium cadmium or argon fluoride lasers, this kind of lasers can be employed to scan a laser spot across the surface, and this is typically controlled by software which contains the photomask design. So, here also you can see the mask is there, then you have a lens which can actually focus it on this particular chip area. And what is this? This is basically a photoresist. Below that you have the oxide film, and then you have the wafer. So, electron beam writing is chosen for achieving smaller features when necessary. So, that you will see that that with lithography, photolithography, the minimum feature size, as you can understand, is diffraction limited lambda by 2. So, when you use electron beam writing, you can actually reduce the smaller feature size, okay, or you can go down to even further smaller sizes. The next method that you can think of is this contact photolithography. So, what happens in contact photolithography? Okay, so you have a substrate, you have a photoresist on this, and then you have a mask, and this you are actually doing UV illumination. So, this contact photolithography technique is widely used in research labs, and it involves placing the photomask in physical contact with the photoresist coated substrate. So, here you see there is no physical contact, right, the mask, and then there is a lens, and then you are just doing focusing. So, it is not actually the mask is not touching your photoresist coated substrate, but here it does. Okay. So, the extent of contact is critical as it determines the resolution of the feature that can be imaged. Okay. So, when you put it on top, the resolution matters. The critical dimension is used to describe the width of the smallest line that can be printed in this kind of photolithography. So, that is called the critical dimension. So, why this contact photolithography is used? They are commonly used or practiced today also, mainly in the applications which require thick photoresist or double sided alignment and exposure. Some examples could be in advanced 3D packaging, optical devices, MEMS applications, etc. Now, there could be some small unintentional gaps between the mask and the photoresist. As you see here, there is a small air gap S, okay, and that could lead to diffraction and enlargement of the exposed patterns. Okay, that is something you don't like, okay, because you are actually looking for finer resolution. Now, you can do aerial images in contact photolithography, which can be approximated. There is a formula that relates the Gaussian aerial image width to the photoresist thickness. So, the thickness of this photoresist layer is Z, okay, the air gap is S, and the UV light wavelength, if it is lambda, you can find out what is the width of the aerial image of the pattern that you have developed. So, W mean will be typically 3 by 2 square root of lambda S plus Z by 2. Okay, that gives you a formula. So, that relates the Gaussian aerial image width, and you can see it is basically related with this air gap and also the photoresist thickness. Okay. So, the next type of photolithography technique is called projection photolithography. The name itself tells you that you are not actually putting the mask in the contact of the photoresist anymore. You are trying to use kind of a lens, projection lens, as you see here, to do some kind of projection on the photoresist. So, that is how the name has come, right. So, for projection photolithography systems use an optical imaging system to project the image of the photomask onto the substrate from a distance. So, this is kind of popular where you cannot actually go and contaminate the substrate. Okay. So, this kind of system resembles an optical microscope, and the resolution conditions are similar to that. However, the resolution here will be limited by the numerical aperture of the projected beam onto the substrate. So, R, the resolution limit, can be set by lambda by 2 Na. So, why they are used? They are popularly used in semiconductor manufacturing and microfabrication processes, and key applications, as you can see, these are in IC fabrication and MEMS fabrication. So, this is a very commonly used technique called projection photolithography. Now, what do you do to increase the resolution? You can see here that there is some limit on the resolution which is coming from the numerical aperture, okay, of the projected beam onto the substrate. So, in order to increase the resolution of projection photolithography, recently there are different techniques been invented, which are like phase shifted mask or optical proximity corrections, off axis elimination, double patterning, self aligned double patterning, etc. So, we will not go into all these techniques, but we just want to discuss about double patterning technique here, because that is very popularly used. So, double patterning allows the creation of lines and spaces with different widths in the photolithography. So, higher doses result in narrower photoresist lines and wider spaces due to diffraction effects, and by increasing the dose, more areas will receive the threshold dose for dissolution, enabling the printing of smaller lines. And double patterning has a wider range of application. So, they can be used for advanced semiconductor manufacturing or fabrication, you can say. So, examples such as logic memory devices or advanced memory devices can be fabricated using this technique. They can also be used for nanotechnology and photonic devices. So, they are very relevant to us, okay, in this particular course. What you have understood, they can be used for optical resonator, photonic crystal devices and waveguides. So, you can use double patterning for this one. So, there are different methods in double patterning. So, let us look into these 3 different techniques those are used. The first one is called LELE. Okay. So, it is litho etch technique or LELE technique. Okay. So, what happens in this particular case? So, you first do the litho 1, that is the first step. So, the first pattern, which is in yellow, is exposed onto a hard mask. Okay. And then you etch. The first pattern is etched onto the hard mask. So, you get this particular brown shape, okay, patterns. Then you bring the second mask. Okay. So, this is you are doing the second lithography. A second pattern, which is again in yellow, is exposed onto the silicon, that is shown in blue color. Okay. And that actually doubles the pattern density. So, this is how you are actually improving the resolution of this technique by doing double patterning. So, this is how you are doing 2 times the lithography, and that gives you higher density. Okay. And then after this litho, you again do etching. The final double density pattern is then etched into the substrate, as you can see here. Okay. And the remaining mask which are here, that can be washed away, and you can get this double patterned array. So, this particular technique is called litho etch technique or LELE technique. Okay. The second one is called litho freeze litho etch technique, LFLE. Okay. So, here also the first step looks similar. So, you have a litho 1 step. The first pattern, which is shown in yellow, is exposed onto the silicon, that is the blue one here. Okay. And then you do the freeze step. So, here the second step is basically freeze, and you coat with a new resist. Okay. So, what happens in this case, the already developed layer that is shown in yellow is chemically frozen and coated with the second layer of resist, which is shown in this brown color, right. And then you do the litho step again. So, the second pattern, which is shown in brown, is then exposed, and that doubles the pattern density. And in the final step, you etch again. So, you remove the unprotected silicon, okay, with this final double density pattern in a single etching operation. So, you just do one etching and you can get this double density pattern. So, this method is called litho freeze litho etch method. There is also another method called sidewall spacer. So, here you do, in the first step you do litho plus H1, okay, of the dummy patterns. So, what you do, a dummy pattern shown in yellow is basically created on this blue silicon layer, okay, and then you grow sidewalls. Okay. So, a film that is shown in brown is grown around the dummy lines that you see here, and then you do the etch back. So, all the films are removed except the sidewalls. So, the sidewalls are remaining, okay, like this. Then you strip the dummy pattern, that is the yellow pattern is now removed and leaving only the sidewalls. So, you have got this sidewalls. So, and then you can do the etching, second etching, and that will give you this double etched, or you can say the double density array. So, the remaining double density sidewall pattern is etched onto the silicon substrate, and you will get, so from here you can get the double density pattern on the silicon. So, these are three methods of increasing or doubling the pattern density on a silicon wafer. So, this is very commonly used technique. So, this is why we have gone into a bit of details of this particular technique. Now, what is another method of increasing the resolution? You can think of reducing the wavelength of the light that is being used. So, in that case, extreme UV lithography becomes very common approach, because you can use there a light source of 13.5 nanometer, okay, and it is an extremely short wavelength, and that can give you a very fine resolution. So, EUVL, that is extreme UV lithography, is basically used for fabrication of high quality optical components which are used in reflective optics and lenses, and they find applications in advanced imaging systems, space telescopes, very high resolution microscopes and all these things. EUVL is basically employed to create photomasks, diffraction grating with extremely fine features, and these components are essential for applications such as lithography, laser beam shaping, diffraction based spectroscopy, etc. This technique also enables precise patterning of nanoscale structures, so that makes it very essential in nanotechnology applications. So, this technique uses only one mask exposure instead of multiple exposure, and the development of the resist material is one of the critical technical issue in this case, as we discussed, because there has to be some material which is sensitive to this particular wavelength. So, that is the challenge currently, and this material, resist material, is necessary to have excellent characteristics like high resolution, high sensitivity, low line edge, roughness, etc. And remember that in this lithography, the photomasks work in reflective mode. So, the photomasks used in extreme UV lithography, they work in reflective mode. So, let us look into the setup of extreme ultraviolet lithography. So, here you can see in this diagram that extreme UV lithography tool typically utilize a plasma source to generate the 13.5 nanometer photons, as you can see here, and the light from the plasma is then gathered using an optical element called collector. Okay. So, they are these collectors, they gather the light, and then the light is directed into a set of shaping optics elements, like you have got a mirror here and then this. So, this one are also called illumination optics, as you see. So, it goes here, gets reflected to this mirror, it goes here. So, this part is called illumination optics. Okay. And the light illuminates a photomask. As you see here, there is a photomask which is located on a high scan speed vacuum stage. So, this is the vacuum isolation. So, this part is in vacuum. Okay. So, it actually moves in this high scan speed vacuum stage, and then from here it reflects and undergoes multiple reflection, and finally it is being put on this resist coated wafer to make this pattern. Now, the illumination optics that you see here, it consists of multi-layer coated normal incidence mirrors and also grazing incidence mirrors. Okay. And the mask that you see, this mask is basically a 6-inch square, quarter-inch thick, low thermal expansion material, which has got multi-layer reflective coating and also an absorber layer, typically which is made of chrome, and it is etched into the design of a circuit layer. So, what happens, the reflected image of this mask, okay, enters a projection optics. So, you can actually call this part as projection optics, okay, and this gives you a demagnification, typically 4:1, okay, and the projection optics are typically a collection of 6 or more multi-layer mirrors, and they have typically numerical aperture more than 0.25. Okay. And the final image that you see here is focused onto a silicon wafer coated with a photosensitive etch, resist chemical emulsion, or simply photoresist. So, this part also is located on a high scan speed vacuum based stage. So, this is where the wafer will be positioned. So, here you can see this part basically shows you the vacuum isolation. Okay. So, this is also in vacuum. Now, where this is useful, we have discussed. So, this is useful in getting very thin patterns or narrow patterns, because the wavelength that you are using is only 13.5 nanometer. There is another type of lithography method that helps you in achieving your desired resolution, that is called laser interference lithography. So, this kind of lithography is typically used to fabricate photonic crystals, and it is a key technique for creating intricate patterns of metamaterials. So, for the topics discussed in this course, we can see that laser interference lithography looks pretty much applicable. It can also be used to fabricate nanopatterned surfaces for biosensors. Okay? It can create highly ordered and controlled micro and nanostructures on surfaces, and these patterns will find importance in tissue engineering applications as well. So, let us go into a bit more details of this particular technique, because this is very much relevant to the devices we have discussed in this course. So, let us start with the first process, that is the cleaning of the silicon wafer. So, you can see the silicon wafers are ultrasonically cleaned in acetone, absolute alcohol and deionized water for 10 minutes, and then it is baked in a drying oven at 150 degrees Celsius for 30 minutes to ensure it is an absolutely dry surface. And after that, you go on to the spin coating stage, where you are supposed to spin coat the photoresist and do some soft baking. So, here a positive photoresist is spin coated on the polished surface of the silicon wafer using a two-stage spinning scheme, and it is done at 25 degrees centigrade, and you use the spinning speed of 500 rpm and the duration for 30 seconds for the first stage, and then you do the second stage spinning, where the spin speed is 10 times, that is 5000 rpm, and you do it for 60 seconds. So, that is how you do the spin coating, okay, and then you actually do the soft baking. So, what you see, the final photoresist thickness on the wafer is about 1.25 micron. Okay. So, this is the height you have to achieve for the photoresist, and then you can put the coated silicon wafer into a drying oven at 90 degrees centigrade for 20 minutes for this soft baking process. And this is done to remove any residual solvent from the photoresist film, and it also improves the adhesion between the photoresist and the substrate, and it is typically done according to the photoresist manufacturer's suggestions. So, they actually can tell you what is the process for this particular photoresist chemical to bind very strongly with your silicon substrate, and you got to follow those processes. After that, you can go look into the third stage, which is basically exposure and post exposure baking. So, here you can see that the laser interference lithography setup is shown typically like this. So, this is the setup that you can see laser beams are coming from two sides, and then they are interfering, and this is typically the substrate, and here also you can see this is the sample. You have got a laser which has got an electronic shutter. It comes from a mirror 1, it gets reflected, there is a beam expander, okay, and then there is a beam splitter. So, one part of the beam is coming this way, the remaining part goes this way. From another mirror it gets reflected, and you actually generate two laser beams, and that actually focuses at one point where you can create this interference patterns. Okay. So, the sample is fixed on a mobile platform and it is exposed for few seconds. So, typical dosage is 60 to 70 millijoule per centimeter square, okay, to a laser of adequate power. So, in this case what happens, a nano groove pattern can be recorded on the photoresist, and after the exposure is done, the silicon wafers are again baked in a drying oven at 100 degrees centigrade for 10 minutes duration, and that actually eliminate the standing wave effect in the photoresist film. So, once it is done, you go to the next step, which is development and hardening. The photoresist films are immersed into positive photoresist developer for 15 seconds to remove the exposed parts, and they also form the photoresist patterns in water bath at 25 degrees centigrade, and then it is rinsed with deionized water repeatedly. So, this is how you do the development of the patterns, and afterwards you again want to harden it. So, the samples are basically baked in the drying oven at 120 degrees centigrade for an hour, and this enhances the adhesion of the photoresist on the sample surface. So, you can see with this you are actually able to have this particular patterns here. So, this, and after developing you are just left with this particular photoresist pattern, and this is also now hardened. Then you go to the fifth step, which is wet chemical etching. So, we will study about etching subsequently. So, what happens here? The wafers with patterned, so this is the silicon wafer with the patterned photoresist film on top. So, it actually works like a etching mask. Okay. So, the portions which are not, portions of silicon which are not exposed to the etchant will not get etched, but the portions which are open, they will get etched, as simple as that. So, these openings, the gaps, they will get etched out. Okay. So, what are the typical etchant? So, they are immersed, this kind of thing is immersed and etched with manual stirring of a mixture solution of nitric acid with, so this is the percentage, okay, 65 to 68% of nitric acid, then hydrogen fluoride, okay, and then water, this is the ratio, okay, in a water bath at 25 degrees centigrade, and this is the time, around 60 seconds you do it, okay. And after etching, the wafer is basically washed with deionized water, and you will get this kind of a structure. And finally, you have to get rid of this photoresist. So, the residual photoresist films that you have seen in the wet etching phase needs to be removed, but that can be done in this particular stage. So, you see what happens, the reaction products in the textures are removed in positive photoresist stripper. So, this is another solvent that can dissolve your photoresist that you have used, okay, and typically it takes around 30 minutes time. And then finally, you have got this one, you have got a patterned silicon wafer, and this wafer are then dried in the drying oven, and the temperature is set to be around 150 degrees centigrade, okay, and this is done after they are ultrasonically cleaned by acetone and deionized water. So, this is how you get the final patterned substrate. So, this is very useful for, as I mentioned, for photonic crystal structures, okay, and also for metamaterials. So, this is very useful in our case. Now, let us look into the other type of lithography, which is non-optical lithography. The first thing that will come to your mind will be, instead of using photons, can we use electron beam? Okay, so that technique is called electron beam lithography. So, electron beam has been the main technique for fabricating nanoscale patterns. Okay, so electron beam lithography utilizes an accelerated electron beam focusing on an electron sensitive resist. So, in the previous case you used photoresist, which are basically sensitive to the UV light that is falling. Here you have to look for a resist that is sensitive to electrons, and that will help you to make the exposure. Okay. So, you can see this is the pattern, typical electron lithography setup. So, you have got an electron beam source, you have the first condense lens, and you have a beam blanker. So, you get an electron beam, you have the second lens, you have got the aperture, deflector, final lens, and then it focuses and does the patterning. Okay. So, you can see here on this particular diagram how the patterns are created. So, these are basically in the shape of electron beam spot, with a diameter that can be as small as couple of nanometers, and it is scanned through the surface of the resist in a dot by dot fashion, okay, like this, and then you can generate the structure that you want to make. So, you can actually see this is the overall pattern, but every dot is now in one stage you are just getting one dot. So, this is a very fine resolution, you can understand. So, e-beam lithography is used in semiconductor manufacturing to create the photomasks, okay, and they are also very widely used for making any kind of intricate patterns for nanophotonic devices and metamaterials. So, again this technique e-beam lithography becomes a very commonly used technique in our domain. So, here the resolution which is of great importance. As you can see, the resolution of e-beam lithography is of the order of 5 to 20 nanometer, okay, due to the ultra short wavelength of electron, which is in the order of few nanometers. However, the lack of throughput limits their applications within research and mask fabrication. So, you do not actually see large scale fabrication using e-beam lithography. And e-beam lithography is normally used for fabricating prototypes of nanoscale structures and devices, and every research institutions, good research institutions in the world, they have e-beam lithography setup where researchers can fabricate this kind of nanoscale devices and test their prototypes. So, to increase the system throughput, multi-axis electron beam lithography has been proposed, but once only the throughput will increase, okay, then only it can go to the mass fabrication, large fabrication scales. So far the development of the technique in the manufacturing process is still limited. As I mentioned, it is due to the difficulty in developing practical electron beam sources. So, getting this source is not that easy, and in the past electron beam lithography was very expensive and thus it was limiting the access, but recently with the development of scanning electron microscopes, okay, these microscopes were able to be equipped with some pattern generator modules, and this enabled the scanning of electron beam spot within the desired areas to generate nanoscale patterns as e-beam lithography system. So, that has actually helped the electron beam lithography to a great extent. The another non-optical lithography technique is FIB, that is focused ion beam lithography. This is a technique which is used particularly in semiconductor industry, material science, and they are also getting increasingly popular in biological fields for doing site specific analysis, deposition or ablation of materials. So, focused ion beams can be used to create cross sections of materials, devices and structures. These cross sections can provide insight into the internal structure and composition of a sample, making this FIB milling a very valuable tool for failure analysis and material research. FIB can also create nanoscale structures and devices with high precision, and researchers use it to prototype novel nanoelectronic, nanophotonic and nanomechanical devices. So, the setup of an FIB resembles that of scanning electron microscope. However, while SEM uses a focused beam of electrons to image the sample in a container in a chamber, okay, FIB setup uses focused beams of ions, okay, it is not of electrons, it is of ions, okay. So, that is the main difference between FIB and SEM. So, FIB can be incorporated in a system with both electrons and ion beam columns, allowing the same feature to be investigated by using either of the beams, okay. So, you can use either electron beam or ion beam, okay, and you can have this dual functionality, and this is possible because the FIB system works in a similar fashion to a scanning electron microscope. Just that the difference is, rather than using electrons in SEM, FIB using a finely focused beam of ions typically it is the gallium ion, okay, and that can be operated at low beam current, which is useful for imaging, or you can use at high beam current for site specific sputtering or milling. If you want to mill some particular material, nanomaterial, okay, or microscopic material, you can use this high beam currents in FIB for doing it. Okay. So, the resolution in FIB is very similar to e-beam lithography, and you can see an overwhelming use of FIB in the semiconductor industry. So, what are the typical applications you can think of? It can be used for defect analysis, circuit modification, photomask repair, transmission electron microscope sample preparation of site specific locations on ICs. So, all these intricate applications can be done using FIB. So, this is how the process looks like. So, here in FIBL, focused ion beam lithography, the gallium ion, which is basically the primary ion beam, that hits the sample, okay, surface and sputters small amount of molecule material, okay, and you can see this materials leave this surface either in the form of secondary ions, like they can be positive ions or negative ions or neutral atoms, okay, and they can also produce secondary electrons like this, okay. So, as the primary beam rasters on the, or you can say scans on the sample surface, the signal from the sputtered ion or the secondary electrons are basically collected to form a particular image, okay. So, as I mentioned, at low primary beam current, very little material will get sputtered, okay, and you can achieve up to like 5 nanometer imaging resolution in the modern FIB system using this particular technique. However, if you want to do some milling, okay, you have to operate at higher primary currents. In that case, a great deal of material can be removed by sputtering, which allows precision milling of the specimen down to sub micrometer or even to nanoscale. So, this is how FIB milling is very popular. Last but not the least, a very important method in lithography is the nano imprint lithography, okay. So, nano imprint lithography is also a cutting edge technique. It allows creating nanostructures on large surfaces. So, this is how it works. You can take a silicon wafer and spin coat it with some resist, and then you align a stamp to this particular substrate, and then you heat up, okay, you press the mold and the substrate together at that hot temperature, okay, and then you demold the substrate from the master. So, you remove it, then you do dry etching, and that gives you new mold, first generation. This is the dry etching of the residual layer, and then the final etching will transfer the material, okay, you will get the pattern that is transferred onto the. So, on this, when you do dry etching, you finally get this particular pattern transferred onto the silicon. So, as you can see here, this particular lithography relies on the exceptional replication accuracy, which is achievable with the polymers. So, nano imprint lithography is used to fabricate nanoscale patterns on sensor surfaces. So, you can actually make this kind of patterns, and nano imprinted substrates can be designed to mimic the nanoscale topology of natural tissues. So, you can actually go for any kind of complicated design, okay, and this will be very useful for cell culture applications. Nano imprint lithography is used to create diffractive elements, and these have applications in beam shaping, laser beam splitting, and also in holography, okay. So, that brings us to the discussion of different lithography techniques. Now, quickly let us look into the pattern transfer methods, okay. So, after lithography, we have seen that the chemical processes get involved to transfer the pattern into the underlying substrate or the film, and this process is called pattern transfer process. And there is an exception in FIB lithography where the pattern is directly etched without a resist, and the lift up process where the pattern resist is used to dissolve an overlying film rather than etching it. But in other cases you are actually doing this etching process, and this etching process can be categorized typically into wet chemical etching and plasma etching techniques. So, let us look into the wet chemical etching or wet etching first. So, wet etching is basically a material removal process that uses liquid chemicals or etchants to remove a material from a wafer. So, this kind of etching is extensively used in the semiconductor industry that allows you to create intricate patterns and structures on silicon wafers. So, obviously, the same method can also be used for our optical devices and photonic metamaterials. In microelectronics packaging, wet chemical etching is used to shape and modify the dielectric materials such as polymers and ceramics, and it is also employed to structure the surface of silicon solar cells. The specific patterns are defined by masks on the wafer. So, that will tell you about what is the pattern that is going to be etched out. So, materials which are not protected by the masks are actually etched out by the liquid chemicals, and which are protected, they are fine. And these masks are deposited and patterned on the wafers prior to the fabrication step, which is done using lithography that you have just seen. A wet chemical etching process involves multiple chemical reaction that consume the original reactants and produce new reactants. So, this wet etching process can be described in 3 steps. First, you have diffusion of the liquid etchant to the surface that has to be removed, and then there is a reaction between the liquid etchant and the material that is getting etched away. A reduction oxidation, or you can say redox kind of reaction usually takes place, and this reaction entails the oxidation of the material, then dissolving the oxidized materials. And finally, you have diffusion of the byproducts in the reaction from the reacted surface. So, this is how the wet etching process happens, and there are 2 types of wet etching. One is anisotropic, the other one is isotropic. So, as the name suggests, this is how anisotropic wet etching typically looks like. So, here the liquid etchant exhibit varying etching rate on different crystalline phases of the materials, and that gives you high anisotropic. So, anisotropic wet etching agents for silicon will be something like potassium hydroxide, then EDP or TMAH, and they can actually lead to significant anisotropy in the etched surface. So, here you can see that you are planning to etch a 100 silicon wafer with this kind of etching agents, and they create one in a pyramid shaped etch pits which have got flat and angled walls, and typically this angle is around 54.7 degree. Okay. So, as you can see, this is the angle between the etched wall and the surface of the wafer. But when you go for isotropic wet etching, it happens equally in all direction, as isotropic the word means. So, isotropic wet etching employs a mixture of hydrofluoric acid, nitric acid and acetic acid. In short, you can call them HNA, and that is used as the common etchant solvent for silicon. And the etch rate in isotropic wet etching is determined by the concentration of the each etchant in the mixture. So, silicon dioxide or silicon nitride often serves as the masking material, okay, that you see here, that can be used to protect the areas from etching by HNA. And during this isotropic wet etching, the material is removed both laterally and downward at the same rate. So, that will actually give you a broader etch profile. So, laterally in xy direction and z direction the etching happens in same rate. So, that is why it is called isotropic etching. So, this lateral and downward etching occurs in both wet and dry etching processes. And the last method of this etching will be plasma etching. Now, plasma etching, or also popularly known as reactive ion etching or RIE, is a very widely used method for industrial processes for etching materials through opening in polymer masks. So, RIE or reactive ion etching is used to create deep high aspect ratio trenches. So, where it is very thin but very deep, those kind of things you can use plasma etching, and you can create vias, the connectors in semiconductor substrate such as silicon wafers. So, reactive ion etching is very popularly used in semiconductor IC industry, and they are also used to transfer fine patterns from a mask or photomask onto a semiconductor wafer. So, in the field of photonics, reactive ion etching can help us create the waveguides and photonic integrated circuit. So, it is very important process that we should pay attention to. So, this method combines the benefit coming from both chemical etching and physical etching processes, and it offers high selectivity as well as anisotropy. And this high selectivity means it etches only materials with desired composition, just like the chemical etching. Okay. So, let us look into this process here. So, reactive ion etching, as I mentioned, is highly anisotropic, and it primarily etches in a single direction from the mask opening, just like the physical etching. Okay. And the reactive ion process relies on energetic particles generated in a plasma to activate the chemical reaction on the surface. So, this is the plasma, and you can see the ions formed in the plasma are accelerated towards the surface and mask openings in the so this is the photomask and this is the substrate, this will be the opening. So, this is how the ions are basically allowed to enter, and the reactive neutral species are also generated in the plasma, reaching the surface without a preferential dimension. So, when both the ions and neutrals are present, especially on horizontally oriented surfaces, example the bottom of an etched pit, a highly selective reaction occurs, and that actually gives you the removal of the target material. So, as you understand, plasma etching or reactive ion etching is very important in situations where you want to have very deep high aspect ratio trenches, and these are very important for some intricate nanophotonic or nanoelectronic structures. Okay. So, that more or less covers all the topics related to lithography and pattern transfer. As you understand, these topics in themselves are like very detailed. So, we may go into the details of each and every topic, but this is not the objective of this course. This course is just telling you the different topics or techniques which are available in the industry, and you can study about them when you want to actually fabricate your device in the future. Okay. So, with that we will stop here. Thank you for your attention, and we will discuss about nanophotonic characterization methods in the next lecture, and that will also be the final lecture for this course. And thank you. If you have got any queries, you can always drop an email to me mentioning MOOC in the subject line.